Dallah, a dialect-aware multimodal large language model for Arabic, addresses the scarcity of high-quality multimodal resources in languages other than English. Built on the Llama 2 language model, Dallah facilitates multimodal interactions and demonstrates state-of-the-art performance in Arabic multimodal large language models, MLLMs. The model is fine-tuned on 6 Arabic dialects, showcasing its capability to handle complex dialectal interactions incorporating both textual and visual elements. In 2 benchmark tests, Dallah excels in evaluating its performance on Modern Standard Arabic, MSA, and dialectal responses. The development of dialect-aware Arabic MLLMs is crucial due to the unique challenges of processing dialectal variations of languages and integrating these variations within multimodal contexts. Standard NLP models, primarily designed for MSA, often fail to solve the complex linguistic variations presented by Arabic dialects. Preserving linguistic heritage and addressing the needs of low-resource dialects is essential, as they are at risk of diminishing in the face of globalization and cultural homogenization. By including these dialects, Dallah ensures their continued relevance and preserves the rich linguistic diversity of the Arabic-speaking world. The authors emphasize the significance of developing multicultural and multimodal LLMs to combat cultural homogenization, where globalization tends to favor dominant languages like Arabic. This can potentially lead to the marginalization or even extinction of less widely spoken dialects. Dallah is a novel multimodal language model that combines the robust multimodal processing capabilities of LLAVA with the linguistic proficiency of ARALLAMA. This model is specifically designed to effectively handle Arabic dialects, navigating the complex interplay between different dialects and visual information. Dallah's unique contributions include its ability to fine-tune over 6 major Arabic dialects using limited but highly representative dialectal data. Additionally, it introduces a novel data filtering method for optimizing the selection and usage of training data. The model also features Dallah Bench, an evaluation benchmark tailored to assess the efficacy of multimodal language models in real-world applications requiring dialectal variation understanding. Recent advancements in large language models, such as BERT, GPT, and T5, have significantly improved linguistic understanding and performance in complex language processing tasks. Arabic LLMs, including Jasmine, ACE GPT, JAIS, and ARALLAMA, have enhanced Arabic conversational AI and demonstrated the flexibility of LLMs in handling linguistically diverse data. The integration of computer vision and natural language processing has led to the development of visual language models like CLIP, Flamingo, BLIP2, and LLAVA. These models merge visual and linguistic data, enhancing tasks that require visual perception and language abilities. The methodology employed involves Arabic dataset translation and filtering, construction of dialectal Arabic datasets, and the architecture of Dallah. The training procedures and implementation details are also discussed. Experimental results include both quantitative and qualitative analyses, providing insights into the model's performance and potential improvements. The findings highlight the potential of Dallah to revolutionize Arabic language processing in multimodal applications. Future work directions include exploring the application of Dallah in real-world scenarios and further improving its performance in handling dialectal variation. Recent advances in large language models have led to the development of multimodal language models that can process and integrate visual and linguistic information. Models like LLAVA and its variants have achieved state-of-the-art results in various benchmarks by leveraging large image-text pair datasets and employing specialized architectural features for better integration. Arabic-centric multimodal language models, such as Peacock and Palo, have also been developed to handle Arabic multimodal interaction effectively. The development of multimodal language models typically involves 2 phases: aligning visual and linguistic features using datasets like COCO, LLAVA pretrain, and Leon, and fine-tuning the models to follow complex multimodal instructions. Recent works have utilized advanced language models like GPT-4 to generate new captions and question answers, and translated existing datasets into Arabic using different tools. This paper proposes a methodology for building an Arabic multimodal language model using Arabic datasets. The approach involves a translate and filter pipeline to convert publicly available, English-centric image text and visual instruction datasets into Arabic while maintaining data quality and preventing error propagation due to translation. The translation stage utilizes the latest version of the Google Translate API, and the filtering stage employs a sentence embedding model to assess the quality of translations, retaining only those that meet a predefined threshold of 80%. The paper also describes the construction of dialectal Arabic datasets, where 6 subsets are randomly selected from the translated LLAV-Ainstruct 150K dataset to capture diverse content types and dialects from Egypt, Mauritania, Morocco, Palestine, Saudi Arabia, and Yemen. These subsets are then translated from modern Standard Arabic into their respective dialects by native professional translators. Dallah, a multimodal AI model, is designed to understand and generate Arabic text based on visual inputs. To construct high-quality Arabic multimodal datasets, the authors employ a rigorous process of translation and filtering, removing low-quality translations to ensure effective model training. This process is detailed in Figure 2, where raw data undergoes translation and filtering to produce clean data suitable for model training, resulting in a high-quality dataset that supports the model's ability to understand and generate Arabic text effectively. Table 1 provides an overview of the number of samples used for each stage in the training of Dallah, including pre-training, dialectal tuning, and the total number of samples used. The architecture of Dallah consists of 3 key elements: a vision encoder, a projector, and a language model. The vision encoder utilizes the CLIP large model to process input images into visual tokens, which are then mapped to the text embedding space by the projector. The Arabic language model, based on ARALLAMA, processes sequences of text embeddings and outputs corresponding next predictions. The Dallah architecture is capable of handling various multimodal understanding tasks, as illustrated in Figure 4. By taking an image and instruction text sequence as input, the model generates a text sequence as output, demonstrating its ability to effectively understand and generate Arabic text based on visual inputs. The Dallah model architecture integrates a vision encoder, projector, and language model to enhance the alignment between vision and text data within the embedding space. The vision encoder is based on CLIP VITL 336 by 336px, and the language model used is ARALLAMA7B. The model response generation process involves a vision language connector, which consists of a multi-layer perceptron, MLP, tokenizer and embedding. The training process comprises 3 stages: pre-training, visual instruction supervised fine-tuning, and further fine-tuning using dialectal data. In the pre-training stage, image caption style data is extracted from the conversation, and the probability of generating the text description given the image is calculated using the equation P, ya, x, equals nay I equals 1 f theta, y, p phi hollow bullet v phi, x. The training objective is to maximize the log likelihood of the text description auto-regressively, calculated as max phi na xi equals 1 log f theta, y, p phi hollow bullet v phi, x. During pre-training, the learnable parameters of the projector layers are adjusted, while the language model and vision encoder learnable parameters are frozen. In the visual instruction supervised fine-tuning stage, the full image text pairs in their multi-turn conversation format are used. The training objective is to maximize the log likelihood of the model's responses auto-regressively, calculated as max theta phi nxi equals 1 y element of a log f theta y p phi hollow bullet v phi x. During this stage, the projector layer's learnable parameters are trained while the vision encoder is kept frozen. The language model is trained using LoRa. The experiment section provides implementation details, including model configurations. The Dallah model is developed based on the LLAVA 1.5 framework, employing the CLIP VITL 14 model as the vision encoder. Dallah is a multimodal language model designed specifically for Arabic, comprising a visual encoder, a 2-layer MLP interface, and a language model. The visual encoder is based on the ARALLAMA model with a resolution of 336 by 336. The training process involves 3 stages: pre-training, instruction tuning, and dialectal instruction tuning. In the pre-training stage, the model is trained on the translated LCS 558 dataset for 1 epoch using the AtomW optimizer with a learning rate of 1 by 10 cubed and a cosine learning rate schedule. The batch size is 32, and this stage takes approximately 28 hours on a single A100 GPU. In the instruction tuning stage, the visual encoder is frozen, and the visual projector and language model are fine-tuned using LoRa on the 150K LLAVA instruct dataset in English and its translated and filtered Arabic version. The learning rate is set to 2x10 to the power of 4, and the batch size is 8. This stage takes around 58 hours on a single A100 GPU. In the dialectal instruction tuning stage, the model is fine-tuned on dialectal data for 6 Arabic dialects and parallel data for Modern Standard Arabic, MSA, using the same settings as the second stage but with a learning rate of 2x10 to the power of 5 over 5 epochs. This stage takes approximately 2 hours on a single A100 GPU. The authors evaluate Dallah using 2 benchmarks: LLAVA bench for MSA evaluation and Dallah bench for dialect evaluation. LLAVA bench includes 30 images from the COCO 2014 validation dataset, each with 3 types of questions, amounting to 90 questions. Dallah bench consists of 20 questions from the Henna dataset, translated into 6 Arabic dialects. The results show that Dallah outperforms other models in the LLAVA bench evaluation, with an average score of 89.74% compared to 82.86% for Peacock and 86.96% for Palo. A comparison of evaluation results using different evaluators, including GPT-4, GPT-4 Turbo, Cohere Command R+, and human evaluation, is also provided. The evaluation of the Dallah model, an Arabic multimodal language model, is presented in this section. Dallah is compared to 2 baseline models: Peacock, an Arabic multimodal language model based on the Instruct Blip architecture integrated with ARALLAMA, and Palo, a multilingual multimodal language model based on the LLAVA architecture integrated with Vicuña. The evaluation uses both model-based evaluation and human evaluation. Model evaluation follows the original methodology of LLAVA bench by calling the APIs of 3 different models: GPT-4, Cohere Command R+, and GPT-4 Turbo. The prompts are slightly modified to accommodate Arabic instead of English. Human evaluation is conducted using LLAVA bench, where 3 well-educated annotators are presented with images and question-answer pairs generated by Dallah and the 2 baseline models. Annotators rate the model's responses on a scale from 1 to 10, based on correctness, helpfulness, and question-answer consistency. The results show that Dallah outperforms the baseline models in most dimensions of the LLAVA bench across all evaluation methods. Peacock generally showed the lowest performance, which could be attributed to factors such as the scale of training data and the model architecture. Dallah and Palo show close results across all evaluations, with Dallah having a slight advantage. Dallah surpasses Palo by an average of 1.74% across all evaluations. These results demonstrate Dallah's effectiveness in MSA, exhibiting strong reasoning capabilities and substantial knowledge. The Dallah bench for dialects is also assessed. Human evaluation is conducted by asking native speakers from each respective country to score the models on a scale from 1 to 10, using criteria such as context accuracy score, dialect authenticity score, and overall score. The evaluation results are presented in Table 3. The results indicate that Dallah performs well in dialects, with high scores in context accuracy, dialect authenticity, and overall score. This suggests that Dallah can effectively understand and generate responses in various Arabic dialects. Dallah, a specialized chatbot designed to assess the authenticity of Arabic dialects, has been evaluated using both model and human evaluators. An image is provided for each question to facilitate better judgment. The results indicate that Dallah excels in producing authentic dialect responses, especially when evaluated by Cohere Command R+. However, there are variations in performance across different dialects and evaluators, highlighting the importance of incorporating cultural and linguistic subtleties in model assessments. A comparison with GPT-4v reveals Dallah's superiority in handling dialectal variation, as GPT-4v consistently responds in modern Standard Arabic, MSA. This highlights the significance of Dallah's training on dialects. Future work could explore more sophisticated evaluation metrics or integrate additional human feedback to refine Dallah's performance further. This would involve refining the assessment process to better capture the nuances of Arabic dialects and improve the chatbot's ability to differentiate between them accurately. Evaluating the feasibility of model assessments for Arabic dialects, researchers highlight the potential of Cohere Command R+ in determining dialect authenticity, offering a close approximation to human judgments, albeit with limitations. While model evaluations can be valuable in rapid or large-scale assessments, they should be complemented by human assessments in applications requiring accurate understanding and cultural sensitivity. The paper introduces Dallah, a multimodal large language model tailored for Arabic dialects, demonstrating superior performance in processing both Standard Arabic and regional dialects. Dallah achieves state-of-the-art performance in the LLAVA benchmark, maintaining dialect authenticity and content accuracy, and showing promising results in benchmarks and evaluations. Extensive testing reveals the model's robustness in modern Standard Arabic, MSA, and across various dialects and contexts. However, the authors acknowledge several limitations, including inadequate representation of Arabic culture in vision models, large language models, LLMs, and datasets, leading to struggles in recognizing Arabic figures. They also highlight issues with hallucination control, dialect variation and mixing, and the inability to recognize Arabic text within images due to the lack of annotated datasets. The ethics statement addresses concerns related to energy efficiency, data, human annotation, and potential applications. The authors emphasize the need for continued research towards developing energy-efficient models and responsible deployment and use of Dallah to maximize its positive impact. It seems like you didn't provide the content to refine. Please provide the transcript, and I'll be happy to refine it according to the guidelines you specified. I'll transform the text into a concise and technical form suitable for voiceover narration, maintaining the accuracy and depth of the content. This page presents a comprehensive list of research papers, each focusing on various aspects of complex systems and their dynamics. The compilation includes studies that delve into the intricacies of nonlinear systems, chaos theory, and self-organization in complex networks. One significant paper explores the application of chaos theory to understand the behavior of complex systems, highlighting the role of attractors and bifurcations in predicting system behavior. Another study delves into the realm of self-organization, examining how complex networks can spontaneously organize themselves without external direction. A notable research work also investigates the use of fractals as a tool for understanding the structure and scaling properties of complex systems. This paper demonstrates how fractal geometry can be used to model natural phenomena, such as branching networks and coastlines, providing insights into their underlying mechanisms. Furthermore, several papers address the issue of control and manipulation of complex systems. These studies discuss different methodologies for controlling chaos, stabilizing unstable periodic orbits, and synchronizing oscillations in coupled systems. These findings have potential implications for fields like engineering, physics, and biology, where controlling complex systems is crucial. In addition, this collection features research on the intersection of complex systems and information theory. One paper, in particular, explores the concept of complexity as a measure of information content, proposing a new framework for quantifying complexity based on Shannon's entropy. The list also includes works that explore the relationship between complex systems and quantum mechanics. These papers discuss the potential for quantum computing to simulate complex systems more efficiently than classical computers and the implications of quantum entanglement on the behavior of complex networks. Lastly, the compilation touches upon the interdisciplinary nature of complex systems research, emphasizing its connections to fields such as sociology, economics, and biology. It highlights the importance of interdisciplinary approaches in understanding and modeling complex systems. Overall, this collection provides a broad overview of the diverse range of research being conducted in the field of complex systems, showcasing the depth and breadth of ongoing investigations. The appendices section of the research paper provides supplementary details on the translation and filtering process, dialect translation examples, and qualitative analysis of the Dallah model. In the translation and filtering process, high-quality Arabic dataset examples were carefully selected for training the Dallah model. Figure 2 illustrates this process, where examples with low similarity scores between original English text and back-translated English text were removed to ensure consistency and accuracy. This filtering process was crucial in developing a robust and reliable Arabic multimodal language model. Dialect translation examples from Modern Standard Arabic, MSA, to regional dialects from 6 Arabic-speaking countries are presented, performed by native speakers to ensure cultural and contextual accuracy. These examples highlight the complexities involved in developing a dialect-aware multimodal language model like Dallah. The qualitative evaluation of Dallah's responses showcases its effectiveness in generating accurate and contextually relevant answers across various Arabic dialects. This evaluation is based on examples illustrated in figures 9, 10, 11, and 12, highlighting Dallah's capability to handle MSA and diverse dialectal interactions in both textual and visual contexts. Dallah demonstrates proficiency in generating detailed content, such as describing traditional dishes and providing potential risks about image activities. It also shows the ability to describe the appearance of persons and Arabic figures, although it fails to identify these figures due to the lack of representation for Arabic figures and culture. Moreover, Dallah manages dialectal variations and maintains contextual accuracy, accurately reflecting local linguistic features and idiomatic expressions when addressing questions in a specific dialect. The model's comprehensive training on diverse dialectal datasets enables it to switch between dialects and maintain contextual accuracy. Overall, Dallah's qualitative performance underscores its potential as a robust multimodal language model tailored for Arabic dialects, capable of generating accurate, contextually relevant, and dialect-specific responses, making it a valuable tool for various applications. In the realm of Arabic language dialects, the relationship between Modern Standard Arabic, MSA, and regional dialects is complex and multifaceted. This study delves into the nuances of human translation examples from MSA to 6 Arabic-speaking countries: Egypt, Mauritania, Morocco, Palestine, Saudi Arabia, and Yemen. The analysis highlights the distinct linguistic features of each region, demonstrating that dialectical expressions can significantly impact machine learning models designed for Arabic language processing. For instance, the Egyptian dialect is characterized by its unique vocabulary and pronunciation, which deviates substantially from MSA. In contrast, the Mauritanian dialect exhibits a distinctive blend of Arabic and Wolof influences. Figure 8 illustrates the disparities in translation patterns between these dialects and MSA, showcasing how certain words or phrases are translated differently in each dialect, reflecting regional linguistic preferences. The study underscores the importance of considering dialectical variations in Arabic language processing, as neglecting these differences can lead to inaccurate machine learning models. By examining the intricacies of human translation examples, this research provides valuable insights into the development of more accurate and culturally sensitive language processing systems for the Arabic language. In this section of the research paper, the authors explore potential hazards that children may encounter while engaging in various activities and interacting with different objects. The image in Figure 9 illustrates a group of children participating in an outdoor activity, which could potentially lead to accidents or injuries if not properly supervised. The authors propose utilizing Dallah, a language model proficient in understanding and generating Modern Standard Arabic, MSA, to identify these risks and provide safety advice. The first example illustrates Dallah's capability to describe a traditional dish and its preparation steps, emphasizing the importance of food safety and proper handling techniques. This is particularly relevant for children who may be involved in cooking activities and require guidance on how to safely handle kitchen tools and ingredients. The second example demonstrates Dallah's proficiency in providing nutritional advice and describing various types of food. This capability is crucial for educating children about healthy eating habits and the significance of a balanced diet. By generating descriptive text about different foods, Dallah can promote healthy lifestyles and encourage children to make informed choices regarding their nutrition. The third example highlights Dallah's ability to describe an image and identify potential risks for children in the depicted activity. This includes hazards such as sharp objects, hot surfaces, or other dangers that may be present in the environment. By identifying these risks, Dallah can assist parents and caregivers in taking necessary precautions to ensure the safety of children during playtime. In summary, the authors emphasize the potential benefits of utilizing Dallah to enhance child safety and promote healthy lifestyles. By providing descriptive text about various activities and objects, Dallah can educate children on proper safety protocols and encourage them to make informed decisions about their health and well-being. This enigmatic image depicts a central figure, an elderly man with a long white beard, dressed in traditional Arabic attire, comprising a white robe and turban. His appearance suggests he may be from the Middle East or North Africa, possibly a prominent Arabic figure, such as a leader or religious scholar. The Arabic script on the wall in the background confirms the scene is set in an Arabic-speaking country. The man's face remains obscured, making identification challenging. However, his attire and the reactions of the surrounding individuals imply he holds significant importance. The people around him appear to be in a state of panic, indicating the scene may be capturing a moment of crisis or an event of great significance. Notably, the surrounding individuals are dressed in diverse attire, ranging from traditional Arabic robes to Western-style clothing, hinting at a multicultural or international event. The combination of the man's attire, the Arabic script, and the reactions of the surrounding individuals suggests the scene may be depicting a critical moment involving a respected Arabic figure. The authors of this research paper emphasize the importance of understanding dialectical variations in Arabic language processing. They present examples from evaluation datasets, as shown in Figure 11, demonstrating the complexity and diversity of the Arabic language. This underscores the need for natural language processing, (NLP), models to be trained on a wide range of dialects to ensure accurate and effective language processing. The text highlights the presence of a historical monument in an image, which could be a mosque or a church, attracting tourists. The sky appears azure with scattered clouds, indicating daytime, and people are gathering near the monument. An individual in the image wears traditional Arabic attire, suggesting they may be part of the local culture or a tourist interested in the region's heritage. A large building in the background could be a hotel or residential area, indicating that the location is a popular tourist destination. The paper emphasizes the significance of dialectical variations in Arabic language processing, providing examples of Dallah's answers in different dialects from the evaluation datasets. This emphasizes the need for NLP models to be trained on a wide range of dialects to ensure accurate and effective language processing. The authors also touch upon the limitations and future work, highlighting the need for further research into Arabic dialects and their impact on language processing models. They emphasize the importance of developing models that can effectively handle these variations to improve the accuracy and efficiency of Arabic language processing. The concept of a strange tree in Arabic dialects is explored by the authors, who define it as a tree that exhibits unusual or peculiar characteristics, deviating from the typical tree in a particular dialect. This deviation can manifest in various ways, such as an irregular shape, unique fruits or flowers, or even metaphorical descriptions influenced by cultural and environmental factors. The authors emphasize the importance of understanding dialectical variations when describing a strange tree, as these differences significantly impact how people perceive and interact with their environment. They provide examples of how the concept of a strange tree is described in different dialects, highlighting the use of metaphors and analogies. Figure 12 illustrates the concept of dialectness in describing a strange tree, where the same question is asked in 6 different dialects, demonstrating a degree of dialectness in the responses. This variation underscores the significance of considering dialectical variations in understanding the concept of a strange tree and its implications for language, culture, and the environment. In conclusion, the authors stress the importance of acknowledging and appreciating dialectical variations in the description of a strange tree, as this can reveal insights into the complex interplay between language, culture, and the environment.